One of the most important reasons we go to space is to know our own planet better. Today I'm going to tell you about an orbiting facility that literally watches Earth's biosphere breathe and grow and die with incredible resolution. I'll talk about its profound, existential and economic importance, and about why it's in danger of being lost. Hey everybody, before we get started I wanted to let you know that August 8th was the 94th birthday of Sir Roger Penrose. The work of Sir Roger and his famous Penrose diagram have been an important part of our channel Insane of Curiosity, and to celebrate we have a limited edition Penrose diagram pin. Pin is based off of our original design of the Penrose diagram that is actually featured in the Planetarium at American Museum of Natural History. The pin will only be available via pre-sale through mid-September. We're also offering 10% off for the first 24 hours as well as 5% off all our Penrose-inspired merch. There's links to the merch store in the description. Now on to the episode. Look again at that. That's here. That's home. That's us. In 1990, Carl Sagan asked NASA to turn the Voyager I spacecraft around for one last snapshot of its planet of origin before it began its long, cold journey towards interstellar. The result was this image, dubbed the Pale Blue, and if you haven't heard Sagan's full speech and want existential shivers, there's a link in the description. We normally think of astrophysics as an outward-looking science, but one of the most important reasons to look outwards is to better understand ourselves. And one of the most important reasons to build telescopes in space is to keep a careful eye on the most precious planet in the universe, our own Earth. Historically, a lot of this good work has fallen to NASA because no one else has the same level of joint expertise and experience in both rocket science and planetary science. One of NASA's Earth-watching programs is the Orbiting Carbon Observatory, the OCO program, which is dedicated to high-sensitivity, high-resolution observations of atmospheric carbon dioxide. The program stumbled at first. One never quite made it to orbit after its launch. Vehicle fairing failed to separate. That was in 2009. OCO-2 launched successfully in 2014, and with the spare parts from both 1 and 2 NASA managed to assemble a third instrument, OCO-3, which now resides on the International Space Station. OCO-3 wouldn't exist if OCO-1 hadn't failed, so, silver lining? From now on, if I'm referring to both OCO-2 and 3 I'll say OCO. Despite the rocky start, OCO is performing quite a bit better than expected. It has a pretty remarkable ability that wasn't even planned. I'll come back to that. First, the specs. OCO-2 is part of the A-Train, a close-flying chain of Earth-observing satellites for cross-checks and combined science. This satellite constellation flies a near-polar, 100-ish minute orbit at around 700 kilometers. The orbit is sun-synchronous, which means the path maintains its orientation relative to the Sun, and that helps with the consistency of OCO-2's measurements. 3 being on the ISS has lower, faster orbit. Together, the OCOs produce high-resolution maps of CO2 density across the planet. So how do they do this? When sunlight reflects off Earth and passes back through the atmosphere, each type of air molecule absorbs a particular set of wavelengths, revealing absorption lines, sort of barcode. When that light is broken into a spectrum, CO captures the spectrum around 2 of the infrared CO2 and around 1 of the oxygen lines. The depth of the lines is sensitive to the number of molecules, while their width carries information about pressure and temperature. The oxygen line is useful for things like path length and geometry. With these data, the OCO pipeline applies sophisticated physics like radiative transfer models to solve an inverse problem. What CO2 profile best explains these spectra given the viewing geometry? The result is a stunningly precise average density of CO2 along the column of the observation. These measurements allow OCO to map CO2 column density with a spatial resolution of a few kilometers and a sensitivity of around a part per million. This reveals the sources and sinks of atmospheric carbon down to neighborhood-level precision, and it does this frequently enough to see seasonal swings and year-to-year anomalies. Combined with other atmospheric data, OCO's observations are used to build highly detailed models of the circulation of CO2 around the globe. This is important for knowing not just where CO2 is being produced, but also where it ends up. When OCO2 launched, it executed its intended functions exactly as planned. And then it revealed an ability that no one expected. It could literally see plants breathing, the faint glow emitted by plants during photosynthesis. When chlorophyll is energized by incoming light, most goes to fueling the plant, but some of that energy is quickly re-emitted as infrared light. Sunlight that is simply reflected off the Earth's surface retains the dark absorption lines of the incoming sunlight. But this photosynthetic glow partially fills in those bands, allowing OCO to measure the solar-induced fluorescence. In this way, we can now measure when and how efficiently plants are breathing. This has broad and incredibly powerful applications. Combined with other data, OCO allows us to watch the natural daily and seasonal shifts in plant metabolism across the globe. It also allows us to monitor the health of critical photosynthesizing systems, from forests to savannas to ocean algae to agriculture. For example, OCO facilitates the prediction and assessment of oncoming droughts in a way that was previously impossible. A plant's photosynthesis efficiency drops very quickly in response to stress, for example due to the heat and dryness that precedes a drought. These changes happen before there's any visible change in the plant life. Because OCO can monitor photosynthesis, it can track how vegetation is responding to harsh conditions. It's the response of vegetation often worsens and even causes the drought. As temperatures rise before the drought, plants actually become more productive, and in the process draw water down into the ground. When temperatures then spike, soil moisture has become dangerously low, leading to the onset of flash drought in mere days. SIF monitoring is our best tool for catching this dangerous cycle before it happens. It's not just security from catastrophic failure. OCO also enables us to perform highly nuanced measurements of plant metabolism, which lets us assess stress, forecast growth, and generally do global vegetation health monitoring. Arguably the most important application of this is in crop yields. OCO's SIF data has been used to predict U.S. Corn Belt crop yields down to the county level. It can do this with better accuracy than current USDA methods, and much sooner. It's hard to overstate the importance of this. Besides the obvious fact that we have a lot of people to feed, agriculture is an enormous part of the economy. In the U.S., agriculture and its dependent industries represent several $100 billion to $1.5 trillion in economic activity, depending on how you count, and employ tens of millions of people. More reliable crop yield prediction is ultimately important for everyone, and this benefit is very much weighted to rural communities, and farmers in particular. For example, they often rely on futures contracts, payments based on crop yield predictions, to finance their efforts. Better yield predictions means better financial security for farmers and food security for everyone. A primary goal of the OCO program was to track CO2 for the purpose of climate change modeling and mitigation. However, the program is way broader than this and would be a no-brainer even without the climate factor. OCO can pinpoint carbon sources and plant metabolic activity, which can be a powerful strategic tool both for geopolitical and humanitarian reasons. For example, it enables us to keep track of carbon-intensive activity like urban or industrial development, whether of friends or rivals, with remarkable resolution. It could literally see a single new power plant or large factory, no matter how well hidden. It can also monitor changes in global crop health, enabling the prediction of crop failure and the potential resulting famines and refugee crises. Regardless of what you think we should do about such things, it's always better to know in advance. And heaven forbid a major conflict breaks out between world powers, but if that happens, it seems prudent to retain the ability to sense new industrial buildup, shifts in land use, supply chains, etc., efforts that might otherwise be screened from direct observation. It's amazing that we have this capability. Currently both OCO 2 and 3 are in perfect working order and could run well into the 2030s and further. They were a big investment to build, at around $750 million, however the ongoing cost is relatively cheap. With a combined budget of $16.4 million proposed for this year, a tiny fraction of the potential returns for their benefit to agriculture alone, to say nothing of the much larger risk-cost analysis against existential concerns like environmental and food security, and even defense concerns. Let me reiterate, no nation other than the U.S. nor private organization has anything approaching the capabilities of the OCO program. Nonetheless, OCO was zeroed out in the White House's budget request for NASA this year. 2025, NASA's OCO team has been directed to plan for a mission closeout. That means switching off OCO 3 and deorbiting OC2, burning it up in the atmosphere. This still needs to be approved by Congress, so it's not a done deal. But there's a fair chance that all of these amazing capabilities you just learned about will literally go up in flames. It's not too late, but it will be soon. Now, it is possible to build and launch new facilities. There was a plan to build GeoCarb, a satellite with similar sensitivities to sit in geostationary over the Americas. It would have been a great complement to OCO because it would increase resolution in NASA's home continent, while OCO continues its global surveillance. The project was cancelled due to cost overruns, so currently there are no plans for new OCO-like facilities. If we ever do replace OCO, we'd be much better off replacing it while it's still running. A decade-long baseline of global monitoring. Shutting that down means breaking a continuous time series that future satellites will need for cross-calibration and continuity. From a data analysis perspective, that cross-calibration is incredibly important, to say nothing of the importance of continuity from a security perspective. Sagan usually said it best. Our planet is a lonely speck in the great enveloping cosmic dark. Obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. NASA's oft-stated prime directive is to explore the unknown in air and space, innovate for the benefit of humanity, and inspire the world through discovery. The image of the Earth as a lonely blue speck, barely a pixel across, surrounded by the vast emptiness of space certainly does that. So does OCO's exquisitely resolved surveillance of a living, breathing planetary biosphere, our only known refuge in a vast and inhospitable spacetime. Thank you to Delete Me for supporting our channel Insane of Curiosity.